So my name is Dmitriy Setrakyan. I'm one of the founders of the GridGain systems. I also run product and engineering. And I'm also a PMC at Apache Ignite. And today we're going to be talking about memory-centric architecture and how can it be applied, how can it be implemented within your current use cases. What does it take to develop within memory-centric architecture? What does it take to deploy it, et cetera? But before we do that, I think it's important that we actually look at how we got here. It's not just to take you through the evolution of databases. I think that's been done many times already. It's also to cover the feature set of all the technologies that have been, and all the use cases that have been historically solved within in memory computing ecosystem. Because where we are today, I think, is a end product or a composition of all these features, all these use cases that been solved probably within the past decade. And by the way, how many of you here have actually worked with in-memory data grids? All right, some hands. In-memory databases? Okay. NoSQL databases? All right. So we got a knowledgeable crowd here, so we should do fine. So when talking about in-memory computing evolution, I'm going to use this Homo sapien evolution timeline. So I think one of the basic concepts here is caching. So I think it's important to start from caching. It's important to start from one of the most fundamental concepts. And everybody knows what a caching is, I think. I mean, but I'll just define it just in case. Essentially, caching is software or hardware which allows you to store data closer to your logic, closer to your application, in order to serve requests faster. So basically, like probably the most caching existed probably since the beginning of computing, since the punch cards. I'm not going to focus on caching too much. I'll start with local caching. So I'm not going to go too far down in the history. So local caching is when actually developers started to realize that going to databases is too slow, network trips are too slow, and it's probably more efficient to store data closer to the directly within application. So it's in-application caching, and probably also storing query results for the queries, essentially to reduce load on the database, to help databases cope faster with the data requests. So essentially, the main benefit here is to reduce latencies, to speed up applications. And most of it was done manually, probably with local hash maps or hash tables inside of a code. And the things that didn't solve was the scalability, of course. The local caches did not scale, and that's actually what gave birth to the distributed caches, which is probably something that most of the people use here. Some of the known distributed caches are, I would say, Redis, probably one of the most famous ones, Memcached. There's also AWS Elasticache, and there are probably quite a few more that I'm not listing. And one of the fundamental principles in distributed caching is shared nothing architecture. When we talk about in-memory computing, when we actually store data in memory, it's never purely share nothing. Because memory is a volatile storage. One server crashes. If you don't have a replica on another server, on multiple replicas on other servers, you will end up losing data. So in reality, you never have pure share nothing approach. You also have replicas. But it's nice to talk about it in a pure form. So shared nothing means that the data set is split between multiple servers, and essentially every server gets its own piece. And the more servers you add, the more data you can store. So collectively, you can store infinite amount of data if you keep adding servers. However, on each server, you can only store as much data as fits in RAM. And one of the biggest advantages here is, of course, horizontal scale. So now, and fault tolerance. Now, if you add more servers, you can process more data. If you lose a server, server crash in a distributed system is never a significant event, or should never be a significant event. You should be able to lose servers and to start new servers at will. So for that, this architecture has actually brought in fault tolerance into the picture. So what are the shortcomings of this architecture? Essentially, the simplicity of API. Most of the distributed caches are have very basic APIs. They actually either work with basic key value APIs or basic data structure APIs. So any kind of enterprise level functionality like transactions, like query capabilities, event notifications, collocated processing, et cetera, are not supported. And also lack of persistence. And this actually, persistence aspect is going to come in when I'll be talking about all the in-memory computing pieces. Essentially, when you work with in-memory solutions, most of the time you will get some level of persistence. However, most of the time it will be simply backing up your memory state to disk. And this is done in order to support full cluster restarts. Because if your cluster crashes, memory is a volatile storage, you don't want to lose the data that you had in memory. So whenever you restart, the data gets reloaded back from disk into memory, and then a distributed cache, for example, in this case, will start to operate. So that actually called warm up on restart. And one of the disadvantages with this approach, first of all, you're still limited by your memory size per server, and it takes time to warm up. If you have lots of data to load in memory, it may take time to warm up on during startup. And that brings me also to another step in in-memory computing evolution, which is in-memory data grids. So in-memory data grids actually came in to solve this shortcomings of use cases that were not supported by distributed caches. So it's essentially, you can think about it as intelligent distributed caches or distributed caches with brains. So some of the vendors in the space would be Hazelcast, Gigaspaces, GridGain, and Apache Ignite. And there are probably others I'm not mentioning. It's not meant to be an exhaustive list. But benefits that we are bringing here is exactly what were not, the features that were not supported by distributed caches, which is ACID transactions, query APIs, some level of event notifications, continuous querying. If you're familiar with continuous query, for example, it's a pretty cool concept that allows you to continuously get updates to the everly changing data on the server side. You can get those updates in guaranteed fashion on the client sides. But one of the probably most important concepts of a data grid would be automatic synchronization with databases. If you look at distributed caches, databases had to be synchronized manually. A pattern called cache-aside pattern. Essentially, you update your database, you update your cache, and then you update your database. And if something fails in between, it's your responsibility to synchronize it. When it comes to data grids, database synchronization happens out of the box. If data is updated in memory, the update is automatically propagated to the database. And if the data is read in memory and it's not there, if it's not cached, it will be automatically loaded from database. On top of that, if you want to save time on writing data, most data grids support a write behind pattern for updates. Essentially, all the writes, most of the writes will be batched together and then flushed to the database at once. So various ways to synchronize with the database. So why it's important? It's important because most of the enterprises still use RDBMS or some other disk-based databases as a storage. And a lot of the times, and most of the times, there's a lot of processes that are tied around database. We're talking about technology that's been there for 20 years. You can't just take it away. You have to, even if you want to replace your database, it has to be a very phased approach. So whenever you come to an enterprise and tell them we're going to replace your database, it's going to be a hard pill to swallow. So in case of a data grid, you're actually telling your business, telling customers you can still use your database, but we will make it scalable. We'll make it horizontally scalable by introducing horizontally scalable cache or horizontally scalable data grid on top of it, and by also supporting all the querying capability and the transactional capability in memory. Another main advantage of the data grids is collocated processing, something that was not present in distributed caches as well. And what collocated processing means, if you work with databases, most of the time you will query your data, you'll get it to the client side, and you will have to process it on the client side. When it comes to collocated processing, you are able to send your computation directly to the server where the data resides. So instead of moving data to the client, you're moving computation to the server side. This way, you're able to compute in parallel across multiple servers, and most of the computations are working on the local data. So this actually conforms with the first rule of distributed programming, which is do not distribute. You do not want to move your data to the client side. You want to make sure that all the computations happen on the local data. So this actually is the most scalable approach to compute in distributed systems. You are never going to be able to get there 100%, but if you're at least moved 50% of your computations to the server side, you already made your cluster more scalable than most other clusters in the world. So the shortcomings of data grids, again, the query language is usually custom. Usually joins are not supported. And when it comes to joins, it's very important within distributed systems to look at join support. Because if you're not supporting joins, then you're essentially doing them manually, because the use case doesn't go away. Your business still will require to query 2 tables or 2 types of data at the same time. So in data grids, majority of the times, it would be done manually. So you would query 1 table, bring it to the client, filter it out, then send those filter results to another query, and query that table. That actually doing a join manually, which is very painful. And again, as with most of the in-memory systems, lack of native persistence. Most of the data grids will have ability to copy the memory data set to disk, but you cannot go beyond that. You're still limited by whatever you can store in memory. And another piece in memory computing evolution, by the way, I'm here talking about most of the storage in memory storage systems. So if you have like, where's Spark? Spark is somewhere in probably spanning all of this technologies together. So when we talk about in-memory databases, which, by the way, this technology came pretty much at the same time as in-memory data grids, so you could actually interchangeably put them before or after each other, it doesn't matter. But the main premises of in-memory database, it's essentially in-memory data grid for SQL. If the main API for a memory data grid is key value, which you basically write your transactional logic in some programming language, maybe C#, maybe Java, maybe any other program, maybe C, C++. You compute on your data using some programming language. When it comes to in-memory database, that programming language is SQL. So think about same distributed cluster, except that now you communicate with it exclusively using SQL. You still get the transactional support. You still get scalability, horizontal scale, fault tolerance, but now you're mostly talking in SQL, and that has both its advantages and its disadvantages. Let's look actually at one of the advantages, which is collocated joins, distributed joins, which are, as I said, one of the key features when it comes to distributed systems, when querying distributed systems. For example, if you think about a data set where we have 2 types of tables, countries and cities. Very simple model. And we want to query all the cities that belong to certain countries, right? That's what this query actually does. Queries all the cities that are in Canada and India. It's important that an underlying distributed system can support a basic query like this. If you can't do that, then you're probably introducing a scalability, but you're removing a huge portion of functionality from your application. So how do you support a query like that? For example, in-memory databases that support collocation of data would be able to actually partition the data properly into in such a way that all the cities are stored exactly on the same server as their countries. So countries are and their cities are stored together. In this case, we're able to send a query to all the nodes, and the nodes that will have Canada and India will respond with the cities that belong to Canada and India. So why is this important? Again, all the joining logic happens locally on the server. There's no distribution of a join. If the data was not collocated like this, then you would have to execute a clustered cross product between two tables, essentially moving huge data sets around just to execute a query like this, or maybe storing it on a disk. Essentially, this query execution would go from milliseconds to minutes, and maybe even hours, depending on your data set. So whenever working with distributed systems and distributed databases, and it goes for data grids as well, it's important not only to collocate your compute with data, it's also important for you to model the data properly so you could actually collocate various pieces of data together. So whenever you actually hear a story that we support distributed SQL and all you do is just plug and play our system into any existing database and it will just automatically work, that is almost never true. Because you will run into a case when the data is not collocated unless you actually take care of it. So if you just plug and play it, you'll run into a case where data is not collocated and your queries will execute for a long time. And potentially, actually, instead of adding performance, you'll be removing performance from your system. So it's important when you're moving from a monolithic database to a distributed database to remodel your data so you properly collocate. And what are the shortcomings? Well, one of the major shortcomings, as I mentioned, would be that essentially when you work with in-memory databases, now that it becomes your database. Most of them will have some ability to back up to disk, but again, you're only backing up your memory state to disk. You're not storing data beyond your memory. And since this becomes your database of record, you're actually forced to replace your database. And that becomes a tough proposition. So if you're already running MySQL or Oracle, replacing them within a memory database would be, again, not very easy. So most of the time, these technologies would be more useful probably in the specialized use cases that work together with existing databases or on a brand new project where database has not even been introduced yet. And again, lack of collocated processing is actually sometimes solved in the systems with store procedures. However, in my view, store procedure coding logic in SQL is not probably the most optimal approach. I still prefer the data grid way, where you actually can code your logic in a free form in a language of your choice. But in any case, some of the collocated processing is supported with store procedures. But you're still having this limitation that you're limited by the size of the RAM on every server. So even though you can scale out horizontally, you are not able to store more data that fits in memory or on each individual server collectively. So probably would not be fair to talk about distributed computing without actually touching a little bit on distributed databases. So a bit of digression from in-memory systems, we're going to talk about a little bit about the database ecosystem, which is also important because I think both technologies are converging into one. I think the memory-centric approach is actually convergence of the distributed databases and in-memory data grids and in-memory databases. So when it comes to a distributed database, I think one of the first technologies that added distribution was NoSQL databases. Essentially, the problem that was being solved is the scalability of RDBMS systems. Monolithic databases like Oracle, like MySQL, like Postgres were deemed to be not scalable anymore. They couldn't cope with the growing loads and volumes of data, especially with introduction of big data. And that's where NoSQL databases came in. And probably some of the most famous players here would be Cassandra, Mongo. There are plenty of others. But the main advantage that they add here would be fault tolerance and scale. So again, you get unlimited storage by adding more servers. The more servers you add, the more data you can store. There's very little in-memory optimization here. Generally, this type of systems do not support SQLs and do not support distributed joins, which I consider to be a huge limitation. and they do not work with memory very well. So memory is a second-class citizen, and that's why they don't perform as well as a memory system. But they can be used as system of records. In case of in-memory systems, you actually most of the time would use an underlying database as a system of record, because in-memory systems would reside as a caching layer on top of a database. Here, databases are a system of records. Another new technology that is becoming to evolve very quickly in this space is distributed SQL databases. So why distributed SQL databases were not introduced before? They kind of were. I mean, we've always had this clustered MySQL, clustered Postgre, et cetera, approaches, but none of them actually approached it from a collocation of data standpoint, how to effectively execute distributed joins, which is a very important concept when it comes to distributed computing. So distributed SQL databases are attempting to solve that problem. And again, this is not an exhaustive list, but I like Cloud Spanner approach, which is essentially collocation across partitions. And I like CockroachDB approach, which is essentially very similar to Cloud Spanner, but if Cloud Spanner is a Google product that runs on Google Cloud, Cockroach you can install on-prem. Both of those systems are SQL. Both of them support distributed queries. Both of them are horizontally scalable. Shortcomings, again, they are only SQL. So you can't really do any collocated processing. You can't really do any in-memory processing or any type of event notification. Triggers become a problem, so, et cetera. So all the things that were delivered by memory data grids, all this extra functionality, you probably are not going to get with distributed SQL databases. But in any case, it's a very important piece in in-memory in a distributed SQL, distributed database evolution. And to distribute SQL database in this fashion is not easy. It's a very difficult task, especially when your data has to be transactable, and when your data actually has to be stored in distributed write-ahead logs across the cluster, and your indexes have to be distributed, et cetera, et cetera. It's a hard problem to solve, and that's why it took a while for these products to emerge, and we're finally seeing distributed SQL databases to begin come around within probably past 2-3 years. And that's where I would say what brings us to a memory-centric approach. So what does it mean to have a memory-centric architecture? Essentially, all these features that I've listed that were introduced throughout the memory computing revolution, or throughout the database revolution, should be solved by memory-centric architecture. A memory-centric architecture is a system that works equally well with memory and equally well with disk. At the core of the system, this actually GridGain and Ignite diagram. There are some other memory-centric systems that probably would have slightly different diagram, but this is the one I'm most comfortable with. But essentially at the core, you will always have a memory-centric storage. Memory-centric storage is the one that actually can work with memory and with disk. In our case, it's important that we are able to integrate with third-party database. As I mentioned, for established enterprises, to replace a database is a very difficult task. Essentially, you just never can do it in one go. First, it's much easier to introduce an in-memory layer on top of a database. Learn how to scale your database. Learn how to distribute, to compute in distributed fashion on top of your database. And then maybe after that, you would say, why do I really need this database? I'm doing all the logic in a distributed fashion already, and maybe you're going to start phasing out your database at that time. And that's why it's important that a native persistence is supported by the system. So Ignite and GridGain actually have its own native persistence. So unlike most of the in-memory systems that can store only the memory state on disk, we can actually grow past the memory. We can grow beyond memory on disk. So that's basically the core principle. And if you assume that at the core you have this memory-centric storage that actually talks equally well to memory and to disk and to third-party databases, then everything else becomes an API on top of it. A memory-centric system like ours actually can support SQL, including distributed joins, including SQL updates, DMLs, SQL alter statements. So essentially, you could talk to the system using just purely SQL. However, I would say in today's computing projects, you rarely just have just one use case. You probably have more than one. Sometimes SQL may be the best solution. Sometimes key value may be the best solution. Sometimes you may have transactions that you want to execute in code. Sometimes you may have a collocated logic that you want to execute across a computational cluster. Maybe you want to deploy services. Maybe you want to do machine learning in a distributed fashion. Actually, machine learning is actually yet another cool technology that follows this principle of collocating of computation and data, because we've grown past the scenarios where the model sets can reside on one server. Now we have to distribute model sets because they've grown too big. And that's why collocation and machine learning is also very important. So all these technologies can now sit on top of this memory-centric storage and enjoy this capability of being fast in memory, or maybe slower when the disk is involved, by being able to store more data. Some of the basic features of a memory-centric storage. One of the probably, so essentially, think about it as a page memory that can expand to disk. If you work with a virtual memory, if you're familiar with a virtual memory is actually ability to expand to disk whenever you run out of physical memory, physical RAM. So it's still volatile, because whenever you restart your server, you will lose the physical RAM state, and therefore the rest of the state becomes meaningless. In case of durable memory, you actually have the full state on disk. And memory becomes a caching layer, or maybe a full copy of the disk. You actually have a freedom of picking and choosing how you want to deploy it. From a transactional standpoint, the storage is transactional, so you still have write-ahead logs. You still have this main storage, where at some point write-ahead logs get checkpointed to the main storage. You still have indexes that you have to store in memory and on disk. But it's also important that the data is stored in memory in the same format as it's stored on disk. You want to make sure that you avoid any type of necessary serialization and deserialization. So whenever you load, whenever you actually have hit a page request, if page is not in memory, it should be automatically mapped from disk. You should not have to deserialize it, which is very time consuming. The storage should be off heap. Again, we're working with huge amounts of data. We're working with memory spaces that probably exceed 64, maybe 128, and even above gigabytes of storage. And we all know that Java virtual machine is not going to cope well with those with that much memory. You will run into significant garbage collection pauses. So it's important to store data off heap. So Apache Ignite and GridGain actually the page memory architecture, the whole page memory space is stored in off-heap storage. And if you do require some off-heap concept, we also have a concept of on-heap caches, just in case if you really need a deserialized form of that data to be available locally. And another important aspect that's been solved by this architecture is instantaneous restarts. As you remember, most of the in-memory systems require reloading of the data from disk to memory upon startup. Here, the system works equally well with disk and memory, so there's no need to load the data in memory to execute a query, to execute any cache operation, to execute any piece of logic. So essentially, the system becomes fully operational instantaneously once you bring it up. And then as you keep querying, keep accessing data, the caches begin to warm up in the background. So as you start using your system, it gradually becomes faster and faster. Also a very important slide is how a memory-centric architecture works with disk and works with memory. As I mentioned, you never have just one use case. You never have just purely memory use case, or you never have purely disk use case. Most likely, within a project or within multiple projects in your organization, you are going to touch across every single use case here. So one of the most basic one is pure in-memory use case. Memory is used as a primary store. There's no disk backup. Essentially, you would use, this is the fastest use case. You never have to synchronize with either database or with disk. So generally, this type of approach is used for volatile data that usually can be reloaded from somewhere else in case of a crash. But you do want to avoid any type of persistent synchronization for performance reason. So that's a purely distributed, data grid distributed in memory database type of use case. The next mode, I would call it, is is the same as the first one in memory, but now you're integrating with an underlying third-party database. So the superset of the data is stored in the database, and the in-memory system, in-memory distributed cache is used as a caching layer on top of that database. So main advantage here is, of course, you get to reuse your database. You don't have to rip and replace it. The disadvantage here is that the superset is still in the database. So if you're issuing a query in this use case, the query will be able to only analyze and query the set that is in memory. It will not know what is in database, obviously, because it never touched that data. However, a very useful approach to actually introduce an in-memory system into your organization because you don't have to change your database at all. Apache Ignite, for example, will automatically integrate with any RDBMS or database or Cassandra from NoSQL space. Now, in-memory plus full copy of disk. This is mainly for in-memory database use cases, and some in-memory data grids will have it. Essentially, a disk is used as a backup of memory to support cluster restarts. If your full cluster crashes, you're able to reload it from disk. And then the final use case is when you have 100% of your data on disk and only a portion of it in memory. It's a memory-centric kind of distributed database use case. This approach would be slower because now you will have cache misses that will have to be reloaded from disk. But now you can store much more data that can fit in RAM. For example, if you have historic data that you need to analyze that may be in hundreds of terabytes or in petabytes, you will never load that in memory, or almost never, actually. We have a customer that did load all of that in memory, but generally speaking, it becomes too expensive of a proposition to load this type of data set in memory. And this actually is a good opportunity to store data on disk, have a available in memory cache. You can allocate as much memory as you like. The more memory you allocate, the better the performance you will get. And a memory-centric system, a memory-centric deployment will have probably multiple data sets in any of these tiers. You will have some data sets that are purely in memory. You'll have some data sets that integrate with third-party databases, and the data sets that have their own storage. It's important that you can query across these data sets in one system, and it's important that you can transact across these data sets in one system. And that's what an ideal in memory-centric solutions should provide. So essentially, it's all the deficiencies that were present in the architectures and technologies introduced before should be solved by a memory-centric approach. Also, I've been to 3 presentations today. Everybody had an HTAP slide. So I think, why should I be any different? So HTAP is essentially an intersection between analytical and transactional processing. And to be honest, it's a very useful concept, but a lot of transactional systems, a lot of systems that are very performance sensitive will be very careful, will think probably twice before introducing analytical ad hoc queries into a production deployment. For example, most of the banks that process customer transactions will not introduce ad hoc ability to execute ad hoc analytics on their production system. However, they will benefit from non-ad hoc analytics. They will benefit from predefined queries that they know in advance will not hog the system. And those type of real-time analytics are important for making real-time decisions, real-time advertisement, real-time customer suggestions, et cetera, or maybe a real-time fraud analysis, et cetera, et cetera. So that's where HTAP really brings value, is when you actually can control your analytics, so you don't bring you don't reduce the throughput of your system, and you still are able to analyze your data. However, when you do need to have ad hoc queries, you can still use HTAP. However, you probably will have ETL because you now have some data sets that are in memory, some data sets that may be in petabytes that are on disk. But since you are not going to be willing to risk the in-memory performance, you may have to copy some data from one storage to another. So in any case, whether you use it in one database or across multiple databases, it's important that your system supports this functionality. And memory-centric architecture actually is ideal for it. Because you could, whether you want to do it in one storage or across multiple storages, you can still do it within one platform and within one API, within the same set of functionality that is provided. And finally, to summarize, probably I'm going to finish in about 2 minutes and probably will give you about 10 minutes of your time back. Probably to summarize, I think here's a basic feature set of most important features of data storage, distributed data storage systems, and some of the most known technologies in the space. And actually, if you go from left to right, it actually also reflects a timeline. So we started off with RDBMS systems, which were very good with transactions, with SQL, which were able to store data but could not scale data. You will never see, or I should never say never, but you will probably not going to be likely to see an Oracle cluster of 100 servers. You will not probably, so in an RDBMS case, adding a new server does not mean you can process more data. It basically means you can just recover from this server in case of a first server crashes. So RDBMS systems are not scalable. They're fault-tolerant, but they're not scalable. And that became a problem when big data came around, and that's when NoSQL databases came up. They became scalable, but now they're not transactionable. That's where eventual consistency came around, and you had to make transactional sacrifices or consistency sacrifices in order to achieve horizontal scale. And also, they weren't in memory, so the performance was not still as great. And then in-memory data grids and in-memory databases came in, which said, OK, we can be fast, we can be scalable, we can still transact and query, use SQL in memory, et cetera. But now you're going to have to sacrifice persistence because it's very difficult to actually introduce distributed SQL, as I mentioned, and distributed persistence that is synchronized between memory and disk. And then that's exactly what driven us in GridGain to introduce this memory-centric approach, which should actually remove all these deficiencies from all the sacrifices, should remove all the sacrifices that you had to make before. So that's actually my last slide. If you have any questions, I'll be happy to answer.